Okay, so if you remember, we were looking at the recycle reactor. Blood flow with recycle. The inlet here, the outlet, which we call F, is 1, 0.2, and 0.3. And we had a recycle ratio, R. That was defined as 3 over VF. And R could go between 0 and infinity. When R was 0, then the V3 is 0, so we just have a simple blood flow reactor. When R is infinity, then we have nothing coming out, and it's just total recycling. And we determined the governing equation, or the design equation for this reactor. So we have some reference state, which we call 0, which need not be, may be, but need not be the same as the end state. Again, V over FA0 is equal to R plus 1, the integral from R xf plus xa over R plus 1 to x f dx minus Rn. And we had a graphical interpretation here. Let's just notice a couple things. This is the same thing as x1, x at point 1, and this is the same as x at point 2. And we noted that the actual equation for the blood flow reactor, this particular reactor, the equation was V over FA0 was equal to, V over FA0 prime was equal to the integral from x1 to x2 dx over minus Rn. So x1 became this, x2 became that by a very long derivation. And we noted that FA0 prime, what was the physical meaning of FA0 prime? Let's start from the third row this time. At the end, what was the physical meaning of FA0 prime? Did you look at your notes before coming to class? You obviously didn't look at them well if you don't know what FA0 prime was. Next. Hello? Did you look at your notes? Please leave. Next. If you haven't looked at your notes, you can go now. Anyone who hasn't looked at the notes can leave. If you looked at your notes, you'll know the answer to this. If you haven't looked at your notes, you don't know the answer. What's FA0 prime? What is it physically? Not the formula. What does it mean? What does it mean? I can't hear a word you're saying.
It's FA1 evaluated at the reference state.
It's FA1 evaluated at the reference state. This class doesn't seem to understand what looking at your notes means. There will be a quiz the next class, and every class following that, until you look at your notes before you come to class. Is that clear? And the quiz will start at 9:15. If you miss the quiz, you get a 0. Is that clear? Yes? You guys are responsible, by the way. FA0 prime is x1 evaluated at the reference state. Why x1 evaluated at the reference state and not x in?
Because if you see the dash box between the recycle, then in and out is like going into a reactor and go out is like a reactor.
I'm sorry, I didn't understand. I didn't see any dash box.
Meaning, if you see the recycle reactor as a dash box, and seeing a recycle reactor because it's a dash box, then and we can suppose that the production points could be back to the reference points.
I didn't understand that. If I get consistent like this of no one knowing what we did in the last class, I will just lower everyone's grade 1 grade. Because it seems to be universal. Nobody is prepared for class. If you don't prepare for class, you will fail. You understand? I don't care if you have straight A's until now. If you don't prepare for class, you will get an F in this class. Can I make that any clearer? Is that clear? If you want to pass this class, then you would better look at your notes before you come to class. Otherwise, F, 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 F. And if you don't believe me, try me. Okay, well, one thing, the flow rated one is different from point A. Yes, because it also includes point 3. But why do I care? Why am I choosing point 1 rather than point A? Because that's what's entering the plug flow reactor. It'd be nice if you went to my call on you. Right? That's what's entering the plug. What's entering the plug flow reactor is stream 1, not stream in. So it's stream 1 that has to be related to the reference state according to the plug flow reactor formula. So that's why we use an FA0 prime here, and we have that FA0 prime is equal to R plus 1 FA0. Where in related, in at the reference state went back to FA0, and stream 3, because the recycle ratio was R times the flow rate, R times VF, and VF goes back to the reference state as well, so I had an R plus 1 FA0, and that's where this R plus 1 came from. So we have this expression here. And we noted, just in passing, that x2 minus x1, which was xf minus rxf plus xa over r plus 1, when we wrote this out, this was equal to rxf plus xf minus xf, rxf minus xa over r plus 1 was just equal to xf minus x in over r plus 1. As a result, we came up with the graphical interpretation. The graphical interpretation was from the mean value theorem. The mean value theorem said the integral from a to b of f of x dx, the area under the curve, was equal to an average value, c, f of c, where c is some point between a and b. Times b minus a, where f of c was an average value. So we had a graphical interpretation here. We have f, a, b, then the area under the curve was equal to the area of some rectangle, where the rectangle crosses the curve at some point c between a and b, and the area of the rectangle is the same as the area under the curve. The area under the curve is the integral from a to b f of x dx, and the area of the rectangle has the same base, b minus a, and it's the height f of c. So as a result, that lent itself to, well, that told us that this equation lent itself to a graphical interpretation. Again, I am not kidding about people failing if you don't prepare for class. If you're too busy and you don't have time to prepare for class, drop the class now and take it next year when you have time. Because if you continue with the class and you don't prepare, you'll take it next year anyway, because you'll fail. Not a joke. If you want to learn something, you come to class prepared. If you don't want to learn something, you shouldn't take the class. Okay, so let's notice that we can write this, we have v over fa0 is equal to the integral from rxf plus xn over r plus 1 to xf dx over minus RA. This is all reviewed, so you don't have to copy it. Divided by xf minus xn over r plus 1 times xf minus xn. So I want you to just notice what I did is I put an r plus 1 from the numerator in the denominator of the denominator, and I multiplied and divided by xf minus xn. Now I did this so you would see what's going on here. What you can see here is this equation now, this particular square bracket, is exactly in the form of the mean value theorem. It's the integral divided by b minus n. The integral from the lower limit to the upper limit divided by the lower limit minus the upper limit. The lower limit minus the upper limit is exactly this. So this is the average value, average in the sense of the mean value theorem, of 1 over minus RA between x1 and xf, or x2. And now that's multiplied by xf minus xn, not by xf minus x2. Let's call this xf. Not by xf minus x1, but xf minus xn. Let's draw a picture. Minus 1 over RA versus XA. Presumably we have some more interesting looking curve that looks like this. Say x1, xn, x2, which is xf. And what we saw is that x1 was somewhere in between. It was rxf minus xn, depending on where R was. I could dial by changing R. I can move when R goes to 0, then I'm at xn. When R is infinity, I'm just at xf. So as R goes to 0, this moves here. As R goes to infinity, this moves there. And I can turn the dial and move it back and forth. And what we can see is that, what does this curve say? This says that V over FA0, which is tau over CA0. That tau over CA0 is the average value of the curve between here and here. So that is, I find the rectangle that has the same area as the area under the curve. And then in order to get this thing, I don't take just this rectangle. What I do is I find a different colored chalk. What I do is I then take this value and extend it all the way across, and the area under here is exactly tau over CA0. So it's the average height from x1 to x2, the average height, and then multiplied by x2 minus xn. Any questions on that so far? Well, there's an obvious question to ask now about designing this reactor. How do I know what value? I told you you can, by turning a knob, the recycle ratio, you can move x1 all the way to the left or all the way to the right. And remember, what we'd like to do is we usually want to minimize tau. So we want to get, if you like, this height as low as possible, because it's multiplied by that whole width. We want to bring this height down. So how do I know how to do that? How do I know how to do that? Clearly, if this is too far to the right in this curve, then the average height is going to be high. If it's too far to the left, the average height is going to be too high. There might be some intermediate value. How do I do that? And so what I'd like to do is I'd like to look for the optimal recycle ratio. In other words, we'd like to vary R and try to come up with the best recycle ratio. What does that mean in terms of calculus? What do we want to do? So how do you do an optimization? How do I minimize? Okay, I take the derivative of what with respect to what? What do I want to minimize? Okay, let me write it. Don't talk too fast. Tau over CA 0 with respect to? No. I take d tau. I think that's always 1. I just said it. No, we're going around the room. I just said it. You weren't paying attention. It's written on the blackboard. R. Optimum recycle ratio. All it requires is reading. First grade. Reading. DR, and we set it equal to 0. Okay, so let's take this thing and take its derivative with respect to R. So I've got DDR of R plus 1 integral from RXF plus XI in over R plus 1 XF dx over minus RA. And now R is here and here, so I use the product rule. What's the product rule? Calculus, what's the product? The derivative of F times G? High school calculus. Derivative of F times G. If you don't know high school calculus, you don't even belong in college, much less in a senior level class. Or if you get nervous when I ask you something that's trivial like that, then you're never going to be able to hold on to a job because your boss is going to ask you questions. And if you can't even answer a simple question that you did in high school, you'll get fired the first day. Derivative of the product. In general, F times G, ddx of F times G. You don't know what the derivative of the product rule is. Let's start with something simple. What's ddx of x squared? ddx of x squared.
Like that was
2x. What's the derivative of f times g? fg prime plus gf prime. This is f, this is g. The derivative of this is 1 times the integral of r xf plus x in r plus 1 xf dx or minus ra. I don't think I've ever had a class where people didn't know how to take the derivative of the product. Ever. I've never had a class where I have to ask more than one person what derivative of fg is. And I've really never had a class where no one knew the derivative of x squared. Plus r plus 1 times the derivative of the integral. We already said what the derivative of the integral was. We have Leibniz's rule. What's Leibniz's rule? Leibniz's rule, please.
Should I apply it to this?
No, just tell me the general rule.
It's partial of f
Total, huh?
from
The left side. Start with the left side.
okay. It's d dr
Well, in general, ddx of the integral from a of
x
to b of x,
b of x
f of xy dy.
goes from a of x to a b of x. The f dx dy plus f of b of x to x
there's another term.
Oh, minus f of a of x to comma b comma s dA dx.
Okay. In this particular case, what has the R in it? Does F have an R, B have an R, or A have an R?
A has
A has an R, and everything else is 0. So these two terms are 0, so I only have this term. So what I'm left with is the 1 over minus RA is the integrand. A value, and it's with a minus sign. Evaluated at A of x. A of x is this. So this is x1. Because this we said is x1. Times ddx of this thing, or ddr of this. ddr. ddr, what's the derivative of a quotient? We already did this row and that row, so let's start with this row. It's the derivative of f times g. F over g.
The denominator squared. I don't know. F prime times g minus g times f prime. Oh, the opposite.
F prime g minus f g prime over
Yes,
g
yes.
squared. Okay, so here's f. So what's f prime? This is f. This is g.
Okay, F prime is
This is f.
okay. X of F.
X f. Times g. Minus f g prime. 1 divided by g squared. Okay, so an r plus 1 cancels. Rxf cancels Rxf. Then I'm left with xf minus x in over r plus 1. 1 over minus Ra evaluated at x1. So I can solve for minus 1 over Ra at x1 is equal to the integral Rxf plus x in over r plus 1 xf dx over minus Ra divided by xf minus x in divided by r plus 1. Well, have we ever seen this expression before? The one on the right? Have you ever seen the expression on the right before? Exactly this. It's exactly this bracket here. This bracket we said is the average value of minus 1 over Ra between x1 and x7. So the average, and this is of course at the optimal recycle ratio. This is a general expression. This is the average of minus 1 over Ra between x1 and xf. This is the value of minus 1 over Ra at x1. And remember, x1 depends on r. So what does that tell me? That tells me I find the best recycle ratio, the optimal recycle ratio, when the average value between x1 and xf is equal to the height of the curve at x1. And that's not the optimal. Let's redraw it. What it says is, when the average value of the curve between x1 and xf equals the height of the curve at x1. So let's look around, say, here. If I look around there, ink chalk. And I look at the average value of the curve. That is, I take this area and I divide it by this length. The average height of the curve between here and here might be, actually I probably should draw it a little further over. Might actually be something like this. I didn't draw it that well. Actually, probably it was a little better before. So here, the average height of the curve between here and here, that is this area more or less balances this area. The average height of the curve is equal to the height of the curve at the left endpoint. Notice over here, the average height between here and here is a lot different from the value at the left endpoint. The optimal recycle ratio, what this tells me, is when the average height of the curve from x1 to xf, the average height of the curve between x1 and xf, equals to the height of the curve at x1. So this is a graphical interpretation of the optimization process. And this tells me that the optimal recycle ratio is here, where x1 is equal to r star xf plus xi in divided by r star plus 1. And that gives me the optimal recycle ratio. So that's the graphical way of doing the optimization. Are there any questions on that? Okay, so now of course mathematically we can just go through and use the formula, but sometimes you get a little more insight by seeing what something looks like graphically.
This is the average value of -1/RA at x1 as a function of r star, not as a function of r.
This is the average value of 1/-RA over a region between x1 and xf.
So it's not, you're not taking it at r star, though, right? You're taking it just for
This function, this thing here, is the average value between x1 and xf. x1 depends on r. When the right-hand side equals the left-hand side, that means I found r star. The right-hand side in and of itself is an average value. I found r star when the right side equals the left side. Okay, so other questions? So if I have a rate curve that looks something like this. By the way, have we ever seen a rate curve that looks something like this? So this is 1/r. If I look at RA, where if 1/RA looks like this, then RA is the inverse versus XA. Looks something like this. Have we ever seen a chemistry earlier in the semester where the rate starts out slow, that gets higher, and then eventually goes down again?
Autocatalytic reaction?
An autocatalytic reaction. So a situation where we might want to use a recycle reactor is an autocatalytic reaction. And that makes sense. Why is that? If we have a simple plug flow reactor, then if we start out, remember, what was an example of an autocatalytic reactor?
yogurt.
Yogurt maker. So if I want to make yogurt, then I start out with a little bit of yogurt and lots of milk. So if I don't have a recycle, or I just have a plain plug flow reactor, the rate of reaction in the beginning is very slow, because I have very little yogurt. So for a while, not much happens, until I build up a lot of bacteria, in which case the reaction goes quickly. If, however, I have a recycle stream, whatever's coming out of the reactor has lots of yogurt culture in it, but not much milk. If I take a little bit of that and I recycle it here, then all of a sudden, instead of having a tiny amount of bacteria, I've got a lot of bacteria. So the reaction can go quickly right from the beginning. So I need a smaller reactor. So it makes sense in an autocatalytic reaction that I might want a recycle just for conceptual grounds. Yep.
So
So why can
Don't ask me what flavor yogurt.
why can the CSTR more potent than the recycled?
Well, the CSTR, you only operate at a single concentration. Now, what you're interested in is not only what you typically, it all depends what you're interested in. If you're interested in getting a fast reaction rate, very fast reaction rate. So let's say this is the rate function. If you use the CSTR, you can use the CSTR operating at this concentration, or this conversion, and I get a very fast reaction rate. However, usually what you're interested in is not just the rate, you're interested in the conversion, in the total conversion. So even though I get a fast reaction rate, I only have conversion that's somewhere here. And here's 0, and here's 1. So I might only, that is, I'll get a quick production of yogurt, but I'll still have half milk. It's hard to sell it when it's half milk. So usually you have two things you want to do. You want an efficient reactor, but you also want to get high conversion. So it all depends on the question you're asking. Sometimes if you're only interested in if you're only interested in high conversion, if you're only interested in a fast reaction rate and you're not worried about the conversion, sure, you would use the CSTR. In fact, let me take that a step further. How could I remedy, let's say I have an autocatalytic reaction and I want to take advantage of the very high reaction rate so I can get a small reactor. But I don't have full conversion. What would I need to do? What would there be, if I had another piece of equipment, could I remedy this problem? What should I do with it? What I'd like to do is I'd like to produce a product, pretty pure product. When I use a fast reaction rate in a CSTR, say operating at this conversion, I get a high reaction rate, small reactor, but I don't have pure product. I have a lot of unreacted reactant there. How can I remedy that situation?
You could another CSTR with a bigger volume.
I could, but then I lose the advantage of having a small reactor. If I can do a separation. So really the best, if separation is cheap, then I would take your suggestion. I would take a CSTR operating at X star. And this is operating at X star. And then I would have a separator with the product here at unreacted A, pure A, here, and then I would recycle that here. So this, of course, if the separation is cheap, your suggestion is better than the recycle reactor. But if separation is expensive, then that's not the case. Okay, well, let's say separation is expensive. If separation is expensive, is there a way with multiple reactors that I can do better than even the recycle reactor, better than this one? When I say better, I mean smaller area. Because here the area is this average height times, it's the area of this rectangle. Is there any way I could do better than that? If I allow myself multiple reactors. Now remember, a lot of times we're stuck with the plug flow reactor with recycle because the CSTR might harm the catalyst. So if I could do this, then obviously CSTR is okay. It doesn't harm the catalyst. Is there another situation where separation is not cheap, where I could still do better than the recycle reactor? Remember, the whole point of doing this graphically is you can hopefully get a little intuition. Typically, since we're looking at tau over C0, we want to minimize that area. Is there any way I can get a smaller area than this if I use multiple reactors? Volunteer? You're just letting me guess. You don't want to tell me how.
I didn't know if you
There's nothing stupid in this class, only not knowing the derivative, how to take a derivative. Volunteer? How might I, with multiple reactors, get an even smaller area than the area of that rectangle?
Could you just do multiple recycle reactors in series?
Well, then I'm gonna get a very complicated graph. And it's not clear that I'm gonna do, and remember, I do best with an optimal recycle ratio. So each one would have to be optimized. It's not clear if I break this up, whether, remember, the advantage here with the recycle reactor is when the curve is not monotonic, when it goes up and down. If I break this up into multiple recycle reactors, there's only gonna be one of them that's not monotonic. So the others wouldn't need a recycle anyway. For this, unless I read that looks like this, but I don't know if it's a system that looks like that.
What if you decrease the distance between X1 and X2?
Well, then you do that by changing the recycle ratio, but this is optimal. And if you decrease it or increase it, it's gonna be worse. That's what optimal means. But that's the best you can do by manipulating recycle ratio.
Can you have sort of like a plug flow reactor coil? Exactly, like, you see, for example, these heat exchangers they use in the breweries, where they, instead of putting a long heat exchanger, they just coil it one on top of the other, and that consumes less area.
Remember, we're not worried about the area of the warehouse where the factory is. We're worried about the actual volume of the reactor. Why is that? Well, typically, reactors are made, typically the materials in reactors could be corrosive, could be caustic. So actually fabricating the reactor is expensive. And the bigger the volume, typically the bigger the surface area, and the surface is often as expensive. So we're not worried whether if we fold the reactor in half and we keep the volume the same, that doesn't matter as far as to zeroth order as far as the manufacturing cost. Obviously, if you have the reactor here in Manhattan, you'd be worried about spaces. But usually we put these in Iowa, where there's plenty of space, or New Jersey. How could we do better? What if we have multiple reactors? You're allowed more than one reactor. But give me a scheme, don't just yell out words.
You have two plug reactors.
Well, we know that plug flow reactors in parallel are equivalent to a single plug flow reactor. So what's the advantage?
In series, equivalent to one.
We said plug flow reactors in series or in parallel are equivalent to a single big plug flow reactor. And it's always cheaper to build one reactor than two. So there's, unless there has to be an advantage to do it.
You see you want
I want to minimize the area.
so you want to minimize tau, right? So we have splitting the volume minimizing tau.
I'm not sure what you're saying.
So the optimum is telling us that the area underneath that we have there, it's equal to the area under the curve. The only way to
The area
minimize
under the curve is when I have a plug flow reactor.
when you're
The area of a rectangle is when I have a CSTR.
exactly.
The area of the recycle reactor is this.
So that's the area for this situation, and we have optimal in the situation here, which we're saying that the area under the rectangle is equal to the area under the curve. So my question is, the only way to reduce that area under the curve is to somehow change the way that the rate is.
I can't change the rate.
That's what I'm saying. So
No,
how?
No, that's the question I'm asking. Yes, you've repeated the question very well. I differentiated already to get the, I differentiated tau with respect to R. X1 is a simple function of R. There's no, what does that tell me? I don't want to optimize X1. I want to optimize tau. Put what in series? CSTRs in series? How many CSTRs? infinite number, then I have a plug flow reactor. What's the advantage? To a plug flow reactor, I could just turn off the recycle if you want to get a plug flow reactor. But that's going to give me the area under the whole curve, under here as well as there. And maybe I didn't draw it right, but that's going to be higher because this is optimized. When R, that is, this value of R star is better than R star equals 0. What other types of arrangements can we have here?
Does the reactor have to be the same kind?
No. I thought you were going somewhere with that question. Think. You're engineers. Your job depends on this.
So let's say you switch out the flow for replacing two CSTRs with different sizes. So this is assuming that you have like depending on the end for
Think, you have a graph here. The reason we do graphical interpretations is so that you can see what you're doing instead of just thinking in terms of formula. Formulas are great when you want to calculate something. But the graphical interpretation sometimes helps you see things that you wouldn't see just by looking at the formula.
So you didn't care about X out anymore?
No, X out is fixed. That's the product specs. The customer wants X out. If you want to produce something else, that's nice, but the customer won't pay for it.
But you can add one reactor.
Yes, I said you can have multiple reactors, but
We
you
can
know,
separate this reaction into two parts in order to get the lower X1 in order to minimize the
which curve are we looking at? This one or this one? Or this one?
the curve where you draw X1 on
This one.
Yes.
Right?
If you separate the curve into two parts,
Separate it into parts. Where do I separate it?
at the minimum,
Separate it to the minimum. So I separated the minimum. So here's the minimum. Now I've got the left part and the right part. Now what should I do?
and then you can, if you do twice the recycle ratio, you could
Twice the recycle ratio? If I do twice the recycle ratio, I'll move X1 over here.
Well, you could probably arrange it in a way that you get a total surface that's smaller.
I know I could. That's the question. Not only I probably can, I definitely can. I want you to help me figure out how to do that. Remember, engineers are supposed to come up with clever solutions. You're engineers, right? Clever solutions. And I'll tell you a story about a clever solution. There, in there's today at, what time was the lecture? At 2 o'clock, there's the first Professor Rolshinar Memorial Lecture. He was a professor, he died at age 88 last year. He was a professor in this department for many, many years. But before he was a professor, he had quite an interesting life story. And he was an engineer, a chemical engineer. He graduated in 1945, a long time ago. And then in 1945, he was in Palestine in 1948 during the War of Independence, the Israel War of Independence. And they didn't have very many bombs, and they only had a few planes. And there was a war going on. And they didn't have enough bombs to use on the other side. But so Professor Shinar was given the task of trying to figure out a way to make things that look like bombs or sound like bombs, even though they didn't explode. And the idea was to scare the enemy. So as a clever engineer, he found that if you drop beer bottles, a certain size, out of an airplane, they make a sound like a bomb, and they blow up when they hit the ground. So what the army of the Haganah used in that war, when they didn't have bombs, they dropped cases of beer outside of planes, a particular brand of beer that made the noise properly. And that was a clever solution. It didn't hurt anybody, and it scared the other side. So you come up with a clever solution when you don't have, you have to work with what you have available. By the way, they went through a lot of beer.
CSTR in the minimum.
See? Go ahead.
And then
Loud so people can hear you.
CSTR and Plethora series.
CS, so the suggestion is, let's try a CSTR followed by a plug flow reactor. And at what conversion is the CSTR operating? At the minimum. So look what the suggestion is. The suggestion is we take a CSTR from X in to X min. Now the area is the area of the rectangle. I can't do any better between here and here. And then between here and here, I do a plug flow reactor. The curve's rising, so I can't do any better than the area under the curve. And that combination is clearly the best I can do with no separator. I can do better with a separator if I have this. So this corresponds to this situation. This one with the separator does even better, but I need a cheap separator. Because this one is a CSTR operating here at the minimum, but the area, because what enters the system is X in, and what leaves is pure product, or X out, so this is even better. This corresponds to this situation. If I have only a recycle, if I have only the recycle ratio to play with, this is the best I can do. If I can do multiple reactors, this is the best I can do. And if I have cheap separation, this is even better. Any questions?
What if we couldn't use the CSTR because it would destroy the catalyst?
Then we're stuck using the recycle ratio. These are just all different possibilities of, depending on what you are allowed to use, what's cheap. These are, if you like, these are all your secret weapons. Other questions? Okay. By the way, apropos of this lecture today, the first Motionar distinguished lecture is a very famous professor from Switzerland who's an expert in control, since someone was interested in control before, who's going to be giving this lecture, Professor Marari. So it's going to be at 2 o'clock in the auditorium in Steinman Hall if anyone's interested. And I think in the beginning he's going to tell some stories, so it's not just to be technical. Okay, so until now, we've been working in sort of a simplified universe of undergraduate chemical engineering. That is, all we looked at were single reactions. In single or multiple reactors. And the reactors were ideal. Ideal mixing or no mixing. Originally, we only had single reactors in the beginning of the semester, but we already added multiple reactors. But the reactors are still ideal, and they're only single reactions. Well, single reactions means all I have to worry about is conversion. I don't have to worry about whether I get the right product or not. Of course, it's much more important to make sure you get the right product than to make sure you have a small reactor. It doesn't really help if you have a small reactor, a really small reactor, and you don't make any product. That's not very useful. You're not going to make any money that way. So what we'd like to do, so we've taken away the single reactor restriction, and now we'd like to take away the single reaction restriction. So we're going to look at issues of selectivity.